Good morning, everybody. Welcome back to the third and almost last lecture of this week. We're getting to the home straight on the knowledge side of this course. Tomorrow there will be something that is not going to be implemented in the bots, so reasoning with uncertainty and vagueness. So that's still relevant for the exam, but not relevant for the bots. So what I've tried to get, again, as I did last week, was to get as quickly as possible into the material that you need for your implementation, for your practical, for your experiments. So we had a look yesterday at the way of representing knowledge so that you could optimize your game playing according to some explicitly, declaratively defined strategies. And you might have seen the announcement that we managed yesterday night to finish the worksheet and the code base for this. As I told you, we have sort of changed the code base from another game, the Planet Wars game. And this Planet Wars game had no opportunity to really use declaratively modeled knowledge. And luckily, the Schnapsen game has that a lot. So if you look back at the lecture yesterday, there were some attempts to give you some ideas of how you could model some information. And I hope that in the coming days and week maybe you'll try to do a bit more and come up with more clever strategies, combined strategies, and run a knowledge-based bot and check out how it performs and how clever your strategies can be as opposed to other strategies such as the random or the RDeep or the learning bots that we're going to look into next week. And all we needed for this was a mechanism to write down the formulae in an unambiguous way so that we had a language that could be understood by a computer and interpreted by a computer so that we could have a formal notion of attainment that was executed by the computer program. But there's still a little bit of magic missing, namely, how do we get from an arbitrary formula in propositional logic, or in logic in general, to an answer, yes or no? So how can we go from the semantics to the algorithm? So the third part of what I consider a logic of an unambiguous language to talk about objects and truth and whatever, a semantics, a form of semantics for it, and finally the calculus. And today we're getting into the question of automated reasoning to calculate whether something is true, whether something is entailed, whether it's satisfiable, and so forth. In order to do that, I want a very quick recap on the semantics of the meaning, the formally defined meaning. And basically, this is all stuff I did on Monday, but this is already, this was relatively fast. So the notion that I'm going to use is an interpretation, which is an assignment of meaning to variables or symbols in generally of the formal language that we've defined. And an interpretation is a model if it satisfies all the axioms of the knowledge base. So this is the basic sort of two sentences. If you understand what this means, you're already most of the way. So we have a formal notion of a model, and now these models, they are all the interpretations of the world that are correct with respect to our commitment, our axioms that we wrote down. And now everything that we want to sort of be entailed, the things that might not be explicitly specified, the implicit specified statements are all those statements that are true in all these models, all the things that are that satisfy all the axioms, all the assumptions that we make about the world. So if we remember this Wampus world example, where you look at all possible interpretations of the world, in this case, we only interested in whether something is a pit or not. So there are 8 different combinations of how the world could look like with respect to these 3 symbols, these 3 variables. Either there is a pit, or there is no pit. So either there's a pit here or not, either there's a pit here or not, either there's a pit here or not. So this gives us 2 to the power of 3 different possibilities to fill in this picture. So we have 8 possible models. And now with respect to these 8 possible models that are shown here on the slide, we can define a notion of entailment. And when I said possible models, then I was talking a little bit too imprecise, I have to say, because I talked about models in the general sense without having any extra knowledge. So as soon as we add more axioms, we have still these 8 interpretations, these possible interpretations, but not all of them are models with respect to the knowledge that we have. So remember that we had the knowledge that here was no information, no sensor information, so this state could not have a pit. So only the states where here is no pit in 1, 2 are correct with respect to my knowledge base, and only those 3 are the models of my knowledge base. And the other 5, they are interpretations that are possible, but that are not, that do not adhere to the constraints that I gave in my knowledge base. So they violate some constraints in the knowledge base. And based on the notion of a model, so all the states, all the possible interpretations of the world that satisfy my axioms, we have the notion of entailment. And entailment means that the statement itself that is entailed is true in all the models. In other words, if the set of models is a subset of the set of models for the formula that we want to see entailed or not. Yeah? So that was the definition of entailment. And how can we do that? We can just check. We can check for all the interpretations of the world that satisfy a certain observation that we want to prove or disprove. And we have to check whether they contain all the models. So this will give us, in a minute, will give us the first naive algorithm for checking entailment. This is a counterexample where we have a set of possible models for a formula alpha 2. So all the possible worlds in which alpha 2 can be true. And it's not a subset of it doesn't contain the models of the knowledge base. So it is not, the formula phi 2 is not entailed. And basically we can translate now this entailment into some action. This is what we do in the Schnapsen game in the new worksheet. And this is done here, so we say state 2.2 is not safe. We cannot prove that it is safe, so we shouldn't go there. So it gives us advice for our decision making. And as I said, we can now use this notion of are the interpretations that satisfy my formula that I want to prove entailment on, is it the superset of all the models of the domain? And this gives us the first algorithm to prove entailment or disprove entailment. And if you look at this example here, we have in the Wumpus world, we have observation, or we have things that can be true or not. So as a breeze, 1, there is a breeze in 2, there is a pit in 1, there is a pit in 1, 2. And obviously we can now enumerate all the possible combinations of these things. So if you remember, we had the observation that there was no breeze in 1.1. So all these models where this is true, where there is a breeze in, we know that they are not consistent with our knowledge base. So they're not even really considered in this table very much. But in principle, we should enumerate all of them. So depending on the number of variables, 1, 2, 3, 4, 5, 6 we have here, we would need 2 to the power of 6 rows in our column, in our truth table. And now we all have to only have to check which of the assignments, so which of the rows in the truth table are models of my knowledge base and which ones are models of the assumption. So, and then check whether they are subsets of each other. And basically, we wanted to check whether alpha 1 is entailed by knowledge base, the knowledge base. And there are several of the states here in which alpha 1 is true, namely these 3, 1, 2, 3, and the one underneath, which is in the graphics these 3 states plus this one, I believe. Or plus this one, sorry, this one, the one in the middle. And now we can look at which are the models of the knowledge base, and this is the 3 in the middle. And we can check that these 3 are a subset of these four of all the possible assignments. So we just have to check per row in principle of our truth table whether if this is true, this also must be true. It's a very simple algorithm that you could write down in 5 minutes. The problem with this algorithm is, of course, as I said, you need it's exponential in the size of the number of symbols that you use. And if you look at a realistic problem like the Schnapsen case, if you manage to look at it, we're looking at more like hundreds of variables or even thousands of variables in this case, rather than 5 or 6, which means that basically this becomes unmanageable very, very quickly. So we need to come up with an algorithm that's more clever. And I already promised you that the algorithm that I would introduce in a bit more detail would be one that's really based on search. And basically the idea is that you use a partial assignments. So you start out with these, I said 6, but it's 7 variables. So you start out with one of the values and you check whether you're, with one of the symbols, you make a random choice or an informed choice, and you try to evaluate the space of all the possible assignments to find a model. And you do this in a systematic way. So basically what we're doing is a depth search with heuristics to decide which choice to make first, so that we get to the solution as quickly as possible. One comment before I get into this algorithm, more as a sort of a reminder again about some notions, and these are the notions of attainment that I just defined. But there are other logical notions that are also defined in terms of models of the knowledge base. So the notion of validity is if it's true in all the models. The notion of satisfiability, if something is true in some model, if there exists a model, and unsatisfiability if there is no model. And the good thing is that these notions can be reduced to one each other. So we can show attainment of a formula alpha with respect to knowledge base KB by assuming the negation of alpha, adding it to the knowledge base, and show unsatisfiability. That was what I introduced yesterday, the proof by refutation. So we don't need to develop an algorithm for all 4 of those. And there are many other of these kind of notions that are very similar. It's good enough to develop one and to reduce the problem to the problem for which we have come up with the solution. So the algorithm of Davis-Putnam, Loveland and Locheland, something which I will know what it is exactly in 3 slides because it's written down there, does actually only do satisfiability and unsatisfiability. Basically, you search for a model. If you find one, it's satisfiable by definition. If you can't find one and you have exhaustively searched through all possible models, it's unsatisfiable by definition. And all the other notions will be reduced to this satisfiability. So now the knowledge-based agent that we implement, for example, for Schnapsen, but for other tasks, has to model the general properties of an environment, has to model the specific state it is in, and the transitions it can take, some conditions that are needed, and then apply simple rules, for example, or reason over these conditions. Why are we bothering? So if you look at the bot itself that we published this morning is really simple. So nothing can go wrong. It's just check for consistency with respect to some strategy, and if it's consistent with some strategy, play the card. So the bot itself is very simple, and all the knowledge is explicitly modeled in some extra other place. Now I have to admit that the way it's modeled at the moment currently is not very intuitive, so it's not clear whether it's more efficient to model in this way. But if it was modeled in first-order logic, for example, in an more elegant formalism, and translated automatically, then it would be clear that it would be easy to include human expertise in a very natural way. And we have to look whether we can sort of provide one of these translation algorithms automatically. In the end, that would be really the goal for such an agent. So you would simply model the strategy in first order logic, and then there would be automatically a translation into the formalism that we have provided in the example bot. Look at it, you will understand better what I'm saying about it. But the reason really is you can include expertise, and it increases accountability because you can explain, you can show this is the strategy I apply, and you don't have to show code, but you show some kind of logical formalism that is unambiguous and has a clear form of semantics. So now we move from what we want to calculate to how we can calculate it. And we use a calculus for that, which is another word for an algorithm. And here is a bit of notation that is important. And this is two symbols that look very similar, and they don't come out so nicely in words. So I always use this abbreviation that you can see there. This is the notion of entailment that I've used several times now. And this is the notion of a calculated result. So this is semantic. And this is calculus. So basically, I just talked about this notion. I want to check whether alpha is entailed by a knowledge base. How can I do this? I have an algorithm that shows this. So these are two different things. And you have to be really aware of this, whether there's two bars or one bar, because it makes a huge difference. So the goal is of any logic that this statement is true that I made up here. Namely that if a formula is entailed by, in this case, by an empty knowledge base, this is written here, can we find an algorithm, this is this bit, that gives an answer yes or no whenever the formula is entailed, or whenever the formula is true in this case. So this is would be a notion of validity. So the task is now to find an algorithm that whenever something is entailed, says it is entailed, and whenever it's not entailed, says it's not entailed. And as I told you yesterday, the first order logic method that we have is semi-decidable. So the implication that we have here, stands for if and only if. So bidirectional implication, only works in one direction. So if it is entailed in first order logic, we can find it, we can prove it. But it doesn't work the other way around. If it's not entailed, we cannot not prove that it's not entailed. So from this idea, there come two notions that are very important, and that is the notion of soundness. So if we have an algorithm that only finds entailed formulae, then it's called sound. So that's the correctness of the algorithm. Yeah? The other direction is that if something is entailed, is it also found? So that's the question of a completeness. And then we need a technical notion as well, because we need termination. Because if the algorithm never terminates, then it is not a decision procedure. But if we have an algorithm that sounds, complete, and terminates, we have a decision procedure for a logical system. As I said, first order logic is undecidable. So basically, there cannot be a sound and complete algorithm that terminates. So I can come up with an algorithm that sounds incomplete, but it never terminates. So basically, it runs on and on and on and on. But I never know whether I'm done or not. So that's the problem. Why first order logic, I have an algorithm for finding the right things, and I will eventually find them all, but I can only do that in infinite time, which is not very handy in real life. Yeah? Luckily, we're working in propositional logic now. And in propositional logic, the algorithms that we usually play around with are relatively simple, and they are sound, complete, and they terminate. And that can be proven mathematically that the algorithms that we apply, they always sound, complete, and terminate, which means that they are decision procedures for satisfiability in propositional logic. And there are, in principle, there are two different ways of doing this. The one which I'm going to discuss in a bit more detail, and the one which you also should be familiar with and play around for the exam, is called the Davis-Putnam, this is embarrassing, Loveland-Lodgeman, I don't know how this is pronounced. So this is Davis-Putnam Loveland-Lodgeman algorithm, which basically is a clever way of looking for all through the truth table and check whether you find a model or not. So basically, if you make a mistake in your search, you do a clever backtracking, including some extra heuristics so that you choose the right order for your variable assignments. Yeah. So basically, this is really working on the models itself. The alternative for doing this is applying inference rules. So basically, you take the symbols, the way your axioms are written down, and you try to manipulate the symbols so that you get from one statement to another statement. So remember that last time I said, for example, that there was a rule, I think, in the equivalence rules that alpha implies beta was the same as not alpha or beta. Yeah? So if I have a formula which says A and B implies C, and I want to show that this is the same as not A or B, not B or C, then the only thing I have to do is to apply this rewrite rule. So this rewrite rule basically tells me that I can take anything like alpha and rewrite it as not alpha. So I do take this bit, I rewrite it as not alpha. Yeah, so this was just applying this rewrite rule. And now I need one more rewrite rule, which tells me that this is rewritten into this bit. Yeah, and that would be the rewrite rule that says not alpha and beta can be rewritten into not alpha or not beta. And that's exactly what I've written here. Yeah? So this is a manipulation of the symbols of my axioms. It's a completely different idea. I'm not talking about anything like models or interpretations anymore. It's just it's on the symbol level of my language, of my representation language. If I have time at the end, I will spend a little bit more time on these rule algorithms. Last year we spent time on this. There is one that is very famous, in particular for more expressive languages, which is the resolution calculus, which is the one that most of the automated reasoning tools implements. It's one of those symbol rewriting algorithms. This year we will talk about more on the model side because it fits nicely the search paradigm that we have been working with, and it's the one that the normal set solver in propositional logic nowadays implement. So our approach to deciding satisfiability will be searching for models. So how are we doing this? As I said, the simplest way for doing it is simply enumerating all the models and checking whether the models of the knowledge base also are not models of the things that I want to prove. So are these three models also a subset of these models, which are the four shown there? So this is the dumb model enumeration algorithm, which just says take a model in a truth assignment. If this model makes the formula itself true, then return satisfiability for all, if it does for all formula, and otherwise do unsuch. Sorry, this is incorrect what I just said. Nobody shouted, but that was because I was talking so fast. This algorithm doesn't check for attainment. This checks for satisfiability. So it doesn't go through all the model, all the interpretations, and checks whether they are, but it only goes through all the interpretation and checks whether there is one that satisfies the formula. So this was, I'm sorry, this is an algorithm for satisfiability and not attainment. And what I described on the slide before was an algorithm for attainment. Yeah. So here it would just be, if you want to find something that is consistent with all these things, then you just have to go through the line, have to check whether there's something true. So basically the proof for knowledge base being satisfiable is by finding a line where you get a true here. And this is what this algorithm does. It just goes through all the lines in the table, check whether it finds an assignment that makes the formula true, and if it does, it returns the value satisfiable. And as you can already see that whenever the algorithm terminates with a set, it has basically found a model. So yes, it is satisfiable, so it's sound, because whenever a formula is satisfiable, the algorithm will say that it's satisfiable. And it's also complete because it does it for all the possible assignments of values. So, and as we have a finite number, the algorithm also terminates, because we have only a finite number of rows, and for a finite number of variables, we can only have finite. We can have many, but we can only have finitely many rows in this table. Always 2 to the power of the number of variables that we have. So, because it sounds complete and terminates, so it's a decision procedure, but it's very dumb because it needs exponential time to look through the model space. So we need to do something more clever, because otherwise we'll never finish. And basically what you do is, instead of sort of looking at all the variables, all the assignments one by one, you do a depth first search, so more informed, more systematically, trying to find a possible model of your formula in a more informed way. And then you do some backtracking, which is basically the algorithm that was developed by Davis, Putman, Lodgeman, and Loveland, and which I'm going to introduce now. There is one for which I unfortunately don't have time, which is, I think, a very nice one, which is based on hill climbing, or greedy search in any case, where you basically do a local search. So you suppose that you have an assignment, you check how many of the axioms it satisfies, it might violate one of them, so you try to improve on the assignment that you found. So it's basically guessing and improving the answer, which is an interesting way of search, in particular if you do it in a parallel way. You might find an answer very fast if you have many variables. And if your task is finding a model, so checking satisfiability, that's great, because it usually works very fast. And if you find one, you have found it, so it's a sound algorithm, but it's not complete, because you might guess incorrectly. Or if you want to do it complete, then you need to apply it very, very often so that it converges against completeness. So it's a very interesting way of doing this, these incomplete local search algorithms. You have approaches that work on evolutionary computing, which is a variant of this. So there's lots of interesting variants doing this, but we are interested in the ones that always give us the sound and complete answer, so really deciding whether a formula is satisfiable or not. And that is the ones that I'm going to show you here. And I will show you several versions, and this one is the sort of the first version that was published. It's a rather naive way of implementing this, and you will see later that if you do it more clever, you can really avoid redundancies in your search tree a lot. And here's how this works. So what you do is you have a recursive function that takes as input a partial assignment. So suppose you have a number of variables, v1, v2, v3, or ABC. Let's take ABC, it's always easier than numbers. And you start with assigning a value true or false to one of the variables. So let's say we guess that A is true. Yeah. So then you have your partial assignments that says true, unknown, unknown. If you know already that this partial assignment makes some of your clauses unsatisfiable, then you can return false. So suppose that I have a clause set which, let's see, let's say something like this, and you make the choice of doing A to be true. Yeah, so that would be your partial assignment, true and unknown. Then the first check would be if my partial assignment makes the formula false, then I return false. So this one would be false, so the call ends. If the partial assignment makes the formula true, then I also finish. And otherwise, I choose another proposition, a symbol in my formula and call the procedure again with a random guess of making the formula false. Yeah? And then I do the recursive call with these making it false, and I return true if it returns true, and otherwise I return the other possible option for this particular variable. So that's where the backtracking takes place. So I make the assumption it is 0, and then I go recursively in the depth of my algorithms until I realize, oh, I made the wrong choice. So then I have to make the other choice and do the same again. So this is how this works. Suppose we have a knowledge base with these 4 clauses. I forgot to say this explicitly, but I said it yesterday. But remember that the input of Davis-Putnam algorithm is a formula in closed normal form, or knowledge base in closed normal form. So we have clauses, and they are interpreted to be conjunctions. So it's conjunction of these disjunctions. And they all have to be, in other words, they all have to be made true. There are constraints that all have to be satisfied. So A or B or C has to be satisfied, A or not B has to be satisfied, and so forth. And if you have a formula that's not in closed normal form, you have to apply the procedure that we discussed yesterday in order to turn it into closed normal form. So how does the algorithm Davis-Putnam work? You make a choice. A is your first variable that you want to investigate, so you make a partial assignment, and the choice in the algorithm was to make A false. So that's where you get the red line and the green line. Yeah. So what happens when A is supposed to be is chosen to be false? Do we make anything unsatisfied here? So a formula interpreted to be false in here? No, this one is still possible, this one is still possible, this one is still possible, and this one is still possible. This one even gets true, so we can stop on that one. But when we start with the first one, we basically have to can't decide on true or false because we still have formula that are not decided what they are. So we have to take the next variable and make a choice, decide on what value to give it. Okay, again, in the algorithm, we start with the negator, with the assumption that the variable is false. Again, nothing happens because we still can satisfy them all. So we make the next decision, and that would be C to be false. And here you see that things get wrong because now we see the first one we can't satisfy. It's not interpreted to be true, but it's interpreted to be false. If A is false, B is false, and C is false, then the first clause is false. Yeah? Okay, so we get a conflict, we have to do backtracking. backtracking meant that we now have to come back on our choice on C, the last decision we've made. And basically we have to decide that C is true. But now you see that if C is true, it violates this clause. So basically the choice of C, either true or false, doesn't give us a model. So we need to do backtracking on B. Yeah. So now backtracking on B means we had tried B to be false. Now we have to try B to be true. But you see that this also violates already the second of the clauses. So this one, whatever we choose B to be, true or false, will not get as a model. So we have to do backtracking on A. So the decision that A is false was basically incorrect. So we have to come back on our decision and make a different choice. The other choice, the next choice, is to say, okay, A must be true then. If I can find a model where A is false, we can find a model where A is true, maybe. And again, we start the procedure again by saying, okay, now we make an assignment on B, and we start with the B is incorrect assumption again. And we do the same for C, but then you see that the last one is violated because here C is false and A is true, violates the last one. So we have to backtrack on C, and then we decide A to be true, B to be false, and C to be true. And this returns an assignment that satisfies all the clauses. So basically we found a model. So this is basically standard depth first search, checking for making a decision, a transition from a certain state where we have a partial assignment. We have, in this case, we have 3 choices of variable plus 2 choices of true or false. So we have 6 choices. It's not a fully shown tree search, but these are the choices that are made given the choice of starting with A, B, and C, and then in A and B we start with the assumption that things are false, but there are different ways. You could even do this in breadth first search, but then that would be really stupid. So this depth first search gives us, after looking through almost all of the tree, an assignment for A, B, and C that satisfies all the axioms. That's nice, but it's very inefficient. So to improve this, there are some observations on what happens with these literals in a clause. So literals are atoms, propositions, symbols, or the negation of them. And basically the first thing you could note is that if there is one literal in a clause that's true, the whole clause is true. So if I have, a clause is a disjunction. So basically what I have in a clause, if I have the situation that true or A or B or C, that is logically equivalent with true. Yeah? Because no matter what I choose for A or B, I can always choose true. So basically, this is irrelevant. And as clauses, you can see them as constraints on the choice of your models. And if a clause says true, it's always true. I don't care what assignment you have. I'm always true as a clause. Basically, you can get rid of the clause. So basically, if there is a literal in a clause that's true, then you can get rid of the clause. And if the clause is true, you can just get rid of it. This is what I just said. So if the clause is true, then the formula has the same value if you take it out. Delete the clauses that contain literals. That's basically the rule that you can apply here. If a literal is false, then you still need the clause, unfortunately. But you can take the literal out of the clause. Yeah? So if I now have something like false or A or B, then this is logically equivalent to A or B. So basically I can just ignore this bit. So it's okay to delete the things that you have evaluated to be false from the clause. That's the third rule. And the fourth one is, if a literal is false, and you have a clause which only contains this literal, then you can return false. Yeah? So if I have a clause that says not A, such as this one, and I interpret A to be true, then my entire system is false because I cannot satisfy it ever, because I can never satisfy this clause. Okay? So basically this gets us to this new version of the algorithm. That's Davis, Putnam, Loveland, Lodgeman 2, which takes as input a possible literal and a formula. And what you do first is you remove all the clauses that contain this literal, you shorten the clauses that contain the negation of the literal, and then you apply the same algorithm again. If the formula is empty, then you return true. If the formula contains the contradictory clause, so an empty clause, that's an important difference. If the set itself is empty, or whether it contains an empty clause, then you return false. And if you've done that, once you've done that, you choose a new assignment and you run the procedure in a recursive way again. And then you have the partial assignment per step according to the choice of the literal. So we don't choose per assignment anymore, but we choose the literals in our recursive procedure. So how does it work again? Same example. We start with, because we don't have any information yet, we have no clause that is sort of single. There's no, we don't know anything about negation yet, truth and falsity. So we start with guessing, and we start with guessing A, and our assumption is we make A false. So as soon as we know that A is now supposed to be false in our interpretation, we can do things on the clauses themselves. And we can do two things here. Yeah, the first one is that we can delete the symbol not A from this clause. The same here and here. Because we know that it will never, it will never make the choice, it will never be considered, because this was an A. As we know that it's false, we know that B or C must be true in order to make this clause true. Yeah? And the same holds here for the second and for the third. The fourth one disappears altogether because we've made it true. If we choose A to be false, then the left-hand side of the disjunction is true, so that the whole clause becomes true. So that's already very good. That helped us a lot. So now let's say we have to choose a value on B, and B is supposed to become true now, false now again, which is good news because it sort of deletes this clause, and it just leaves us with these two clauses left over with C and not C. And here you see that we have a problem, because now we can't choose a proper C. Both of them give us contradictions because in both cases we get the empty clause. So we have to backtrack on B. We have to choose B to be true. And basically that gets us into trouble here, because we need B to be false. So we have to backtrack on A. We'll make A true, which means that the first three clauses can go. B, the choice on B doesn't matter. So we make any choice. And now we have to choose C to be true, and we find the solution. So that's already quite good, because it helps us sort of navigate through the tree, but still it's not the golden bullet. And the golden bullet in this algorithm is basically this one, namely the the idea of unit literals and of pure literals. And to keep the tension up in the course, I will explain about the unit and the pure literals after the break at 12. So yeah.